Can anybody tell us what they understand by the buoyant force? You must have seen that in lecture. What is the buoyant force? You haven't seen that in lecture? The buoyant force?
Is it anything that can float in water?
It has to do with floating. Okay, why do objects float? In water, in air, or in any fluid? If you take a coin, okay, a quarter, for example, okay, and drop it in the sea or the ocean, what's going to happen? It's going to go down. It's going to sink, right? But take a much heavier object, um, an aircraft carrier, for example, much heavier than a coin. But if you put it on the ocean, it doesn't sink, it floats. What's the difference? Can anybody explain?
It has to do with the density.
Okay, explain more. That's true.
So if the object has less density than water, it would float, and it would sink if it has more density.
Yeah, that's true. That's exactly right. Okay. So, so which one has less density between the quarter and the aircraft carrier?
The quarter.
The quarter has less density, so it should float or it should sink if it has less density.
If it has less density than water, it's less dense.
So if it's less than water, what's going to happen?
It should float.
So the quarter is going to float then?
Well, it depends, I guess, what its density is.
Okay, so we can add to that. Well, a quarter is not as heavy as an aircraft carrier, but it's more dense. Okay, it's more dense, and because it's more dense, it sinks to the bottom. But an aircraft carrier is mostly empty air, even though it's super heavy, but it's mostly empty air. Okay, it's very huge, and because of its size, its density is very low. Okay, what is the formula for computing the density? Actually, you have it in your lab. Okay, in the file of instructions for your lab, you have a formula for your density. The density is the mass of the object divided by its volume. Okay, you see that the volume of an aircraft carrier is big and it's in the denominator. So whenever you divide by a quantity that's big, you get a small number. So that's why the density is small, and that's why it's able to float. Okay, but the coin has a very small size, therefore a very small volume, and in the denominator, when you put the volume there, the fraction doesn't become small. Okay, so you get a larger density, and that's why it sinks. Okay. But now, it's not sufficient in engineering. Okay, if you want to build a submarine, for example, it's not sufficient to know just what the density is so that the object will float or will sink. Okay, you need more precision. Okay, and you need to quantify the force that will keep the object floating, and then you need to know what force you need so that the submarine, for example, can go down a certain depth. Okay, and to do that, we need the concept of the buoyant force. So what is the buoyant force? Okay, so you have it in your instructions. Okay, so it's equal to the weight of the fluid that's displaced by the object. So the buoyant force on the object is the weight of the fluid that it displaces. Okay, and it is that buoyant force that will come into play when the object is submerged in a fluid. All right. Another example we can give is that of an air balloon. Okay. What happens with an air balloon? Can anybody tell us why an air balloon is able to rise up in the air? After all, what's inside of it is air, just like the air outside of it, right? It's not hot air, yes. So somebody in the chat room says hot air. So what happens if it has hot air? Hot air balloon, yes, that's correct. So why is it able to rise up in the air? Air is also a fluid, right? Just like water. Hot air is less dense. That's true. That's true. It's less dense because it occupies more volume than the same amount of air, but which is not hot. Okay. When you heat up a gas, it expands. Okay. So it takes up more volume. Again, the density. See, the volume is in the denominator. So the volume becomes larger, which means that the fraction becomes smaller. And that's why the density is smaller. Okay, so the air inside the hot air balloon is less dense than the air outside, and that's why the entire balloon becomes less dense, and that's why it rises up. Okay. Okay, good. So I think you understand the concept of the buoyant force. Okay. Okay, so this was the introduction. So I think now we can start with the simulation itself. Let me share my screen with you. Yeah, this is the screen. Okay, so we are taught to click begin. Okay. And click on fluid until it changes to gasoline. Okay. So fluid is here, mercury, gasoline. Okay. So when this bottle goes into the liquid, which is gasoline now, okay, it's going to displace an amount of this liquid, okay? So, which is a fluid. Fluids are liquids and gases. So it's going to displace an amount of this liquid or this fluid if you want. As it goes down deeper and deeper, it displaces more and more fluid, okay? Until it is completely immersed into the liquid, okay? Then at that time, it will have displaced an amount of gasoline equal to its volume, okay? Volume-wise, okay? And the weight of that gasoline, okay? The weight of the gasoline corresponding to that volume displaced by the bottle will be the buoyant force, okay? That will oppose the weight of the bottle, okay? So we want to calculate that. So what are we told to do? Click on fluid until it changes to gasoline. Select Earth, so we are on Earth. The bottle volume must be 500 milliliters, which it is. And the mass, 1,000 grams, which it is. Then we need to click on Start and allow enough time for the bottle to be completely submerged and motionless. Okay. And the graph shows total time 16 seconds. Okay. So there's a graph at the bottom, so you will have to scroll down to see the graph. Okay. So let me click on Start, and then I will scroll down and see what happens with the graph. Start. The bottle goes in slowly. More and more liquid is being displaced, so which means that the buoyant force is increasing, and that shows on the graph. You see the graph at the bottom. Now let's think a little bit. What the vertical axis for this plot says force in newtons, of course, and the horizontal axis is time in seconds. But what force are they talking about here? There are three forces that come into play in this lab. There's the weight of the object that's being submerged. Okay, that's a force, which is the force of gravity on that object, on the bottom in this case. There is the buoyant force, which opposes it, which points upward. Okay, the weight points downward, and the buoyant force in this case will point upward. Okay, I mean there are buoyant forces on the side, but they cancel out. Okay, so the one that matters to us is the one that points upward. And there is also the apparent weight. Okay, the apparent weight of the bottle. Oh, okay. Because you see the buoyant force at least partially cancels the weight or the gravitation force of gravity on the bottle, which means that the bottle will weigh less, okay, inside the liquid. And we call that weight, it's apparent weight inside the liquid. Outside, it's normal weight. Outside in the ambient air, we will call that the actual weight. Okay. So which one? So there are three forces that come into play here in this experiment. There is the buoyant force, there's the actual weight, and there's the apparent weight. So which one of these three forces do you think this plot represents? Anybody, any idea? Can be the actual weight, because the actual weight is supposed to be constant. It doesn't change with time. Okay. Could it be the buoyant force? The buoyant force is supposed to start at 0 because it's the weight of the liquid that's being displaced. At the beginning, at second 0, when the bottle touches the surface of the liquid, well, there is no buoyant force because the bottle hasn't displaced any liquid yet. When it has entered the liquid, let's say 1/10 of the bottle has entered the liquid, then the bottle has displaced a liquid whose weight corresponds to the amount of gasoline that would fill 1/10 of that bottle, because that's the amount of gasoline that it has displaced. And therefore, the buoyant force on the bottle is the weight of that gasoline that's being displaced. But that buoyant force is pointing upward. Okay. And as the bottle goes deeper and deeper into the liquid, the buoyant force increases because more and more gasoline is being displaced. So the buoyant force should increase as time goes by. Okay, but this graph shows a quantity that decreases as time goes by. So this cannot be the buoyant force. Okay, so the only remaining possibility is the apparent weight. Therefore, this is the graph of the apparent weight. All right. If this is the graph of the apparent weight, can you deduce the actual weight of the bottle and the buoyant force at, let's say, at the end of the experiment? Okay, second 16. Can you deduce the, so this is, so we are going to say this is the graph of the apparent weight. In that case, what's the actual weight of the bottle and what's the buoyant force on it, on the bottle at second 16? The formula is buoyant force is actual weight minus apparent weight. Buoyant force is actual weight minus apparent weight. And we are saying that this is the graph of the apparent weight. So what's the actual weight of the bottle? No idea? The buoyant force? The actual weight is the weight, is the apparent weight when the bottle is just touching the water. So when there's no buoyant force on it. So that's at second 0. At second 0, we have an apparent weight. So if there's no buoyant force, then the apparent weight is the same as the actual weight. And so that's 10 Newton in this case, because we are starting with 10 Newton. And the apparent weight at the end of the process is, as you can see, it's about, I'm seeing 6 Newton at second 16, okay, at the very end of the experiment. of this trial. So it's 6. Therefore, the buoyant force is the difference between the two. So 10 minus 6, which is 4. The buoyant force is 4 Newton. Yeah, 4 Newton. Are there any questions? Because this is very important. I'm spending a lot of time on this because the remainder of the lab will depend on how well you've understood this graph. If you understand this graph well, the remainder of the lab should be easy. Okay. And then you are told to click on location to change. So we have to go back, scroll back up, and then click on reset, and then change to the moon, for example, and carry out the experiment again. So let me do this. So click start, click start. See more and more liquid being displaced, therefore more and more buoyant force, and you see how the graph changes. Okay, this is again the graph of the apparent weight of the bottle that we are on the moon this time. Okay, so let me ask you the question again to see how well you have understood this. Since this is the graph of the apparent weight of the bottle in gasoline, submerging gasoline on the moon, and we know that the buoyant force is the actual weight minus the apparent weight. What is the actual weight? The actual weight of this bottle. So which means the force of gravity on the moon, of the moon, the gravitational, so the force with which the moon is pulling on the bottle. I think I have an answer in the chat room. Let me see. I think I can't read. I don't think I can read. I cannot read it. I think while I'm sharing my screen. So you'll have to tell me what it is. I can't read your answers in the chat room when I'm sharing my screen, unfortunately.
Yeah, I was just asking if in this case, the force in the air would be 1.6, and the water would be 1.
Yes. 1.6. The 1.6 Newton. That's the actual force in the air, or actual weight of this bottle. Okay, actual weight. What we mean by that, of course, that's the force with which the entire moon is pulling on the bottle. Yes, that's true. And then keep talking.
And the force in water would be 1 newtons, right?
Yes, the apparent weight after 16 seconds is 1 Newton. Yes, that's true. That's true. And after 16 seconds, because you see it keeps changing, and it keeps changing because as it enters the water, as the bottle enters the water, I mean the gasoline, it's actually gasoline, it displaces more and more gasoline, and therefore the buoyant force increases, and the buoyant force is the weight of that gasoline being displaced. So there's more and more gasoline being displaced, therefore more and more the buoyant force opposing the actual weight, and therefore the apparent weight um, decreases. It decreases with time because the buoyant force increases, right? The actual weight minus the buoyant force gives you the apparent weight. And since the buoyant force increases, the apparent weight has to decrease. That's why you have a decreasing curve. And as time goes by, it goes down until at second 16, you get an apparent weight of 1 Newton. That's true, that's correct. And what is the buoyant force at that time, second 16? What's the buoyant force at second 16 here on the moon? Anybody? What's the buoyant force at second 16? It's the difference between the two, 1.6 minus 1, because buoyant force is the actual weight minus the apparent weight, and 1.6 minus 1 is 0.6. So the buoyant force is 0.6 on the moon. All right. And then you have to do it on other planets, on Mars, on Venus, on Jupiter, on Vesta. Vesta is an asteroid, the asteroid belt. So that's the first part of the lab. Now the second part. Okay, so for the second part, but then at the end you will have to graph all of this. Okay, make a graph of the buoyant force versus the acceleration due to gravity, because with different planets we'll have different accelerations due to gravity, of course. Okay, so we want to know what the relationship between the two is, the buoyant force and the acceleration due to gravity. Okay, and you will have to plot that and give us the equation of the line that establishes that relationship. For reference, if you don't remember how to make such a plot and obtain such an equation, go back to the first lab. I described it in detail using Excel. Okay, and the first lab is posted on Blackboard. The video for the very first lecture is posted on Blackboard, and you can find it on YouTube too. All right, so you'll have to do that. You can do it tonight, and you can do it after today's session, so during the week. Now, the second part of the lab, we want to compare the buoyant force and the fluid density. Okay, so let's restart. So we are going to reset everything. Okay, and we are told to click reset on the lower right and select fluid as gasoline. We have the fluid as gasoline like before. Select location as Earth. We go back to Earth. Earth. The bottle volume must be 100 milliliters. Let's decrease the volume to 100. 100 milliliters. And the mass is 2,000 grams. We have to increase the mass to 2,000 grams. Okay. So then we have to start the first trial and allow 16 seconds to elapse before we read off the values on the graph. Okay. Okay. So let's start. Start. Okay. Nothing. So because it hasn't entered the fluid, apparent force is constant. All right. So what do you see? Can anybody describe what they see?
It's parallel, right?
Yeah. It seems nothing is changing, right? It seems we have a constant graph. We are so seems we have a constant graph. But you can still interpret it, okay? I did that before, and maybe so. Let me do it on Mercury. Okay. Or with fresh water. Let me do it with fresh water. Okay, maybe we will have fresh water. But that's true. What you said is correct. It seems the graph is constant. Okay, but you can still interpret it. You can still tell us what the apparent weight is, what the actual weight is, and what the buoyant force is. Water. So the graph is all right. This one is not quite horizontal, even though it does look a bit constant, but it's not quite. So how do you interpret it in terms of the forces involved? What is the actual force of the bottle? What is the apparent weight at second 16? Because you see the apparent weight changes. The actual force will not change. Okay? It's always the same. But the apparent weight changes. So we are interested in its value at the 16th second. And then what is the buoyant force at that time? So somebody? Okay, I'm seeing the actual weight too. Seems to be 19.5, 20, 19.5. And the apparent weight looks like 18.5 to me, 19.5, 18.5 or 19. So that the buoyant force is the difference between the two. So that would be about 1. So that's what I'm finding. Okay. All right, and then you'll have to do it for the other liquids, other fluids. Okay, for gasoline, for crude oil, and for mercury. Okay, for liquid mercury, and so on. Okay, so that's the second part of the lab, and then of course at the end you will have to plot your data in order to study the relationship that exists between the buoyant force and the density of the liquid. Because for all these liquids, the density is different. The density of the liquid, of course, what we are talking about. Now, the third part of the lab, unless there are questions for the second part. Are there any questions? Then the third part. Third part, quick reset. the select fluid as fresh water, which we already have. Select location as earth, we are already on earth. Bottle volume is 100 milliliters, we already have that. Mass is 1,000 grams. It may be hard to get to 1,000 grams. You see, when I go down, I don't reach 1,000, I go below 1,000. When I go up, I go above 1,000. So what I like to do, or what I did, I restarted the simulation because it starts at 1,000 grams. Okay, so let me close this down and restart the simulation. Okay, if I find it. Let me start sharing and find the simulation first. Okay, I'm sharing my screen with you. I found it. All right. Click begin. So you see, we start at 1,000 grams indeed. Right. So we need the fluid to be fresh water. It is. Select location as earth. We have earth. The bottle volume is 100 milliliters. Can decrease that to 100. It's not hard to get to 100. It gives me 100 exactly. And the mass needs to be 1,000 grams, which it is. So allow 16 seconds to elapse before you reach the values. Okay, click start. Okay, so we get current weight decreases about going into the water. All right, somebody to interpret this graph. Can you see my screen? Can you see the graph? Somebody for an interpretation? Yeah, somebody. So somebody, I have a message, but I don't think I can read it. Okay, okay. 10 to 9. Yes. What do you mean by 10 to 9? What do you mean? That's yes.
The actual weight is 10.
Yes, 10 newtons.
And then you subtract it from the apparent weight, which is 9.
Apparent weight is 9 at 16 seconds. Yes.
And then you would get 1 for the buoyant force.
Buoyant force. That's true. That's correct. So that's all you have to do. Okay, but you have to do it several times for I think okay 7 different bottle volumes. Okay, so this time it's the volume that changes. So basically, you are doing the same thing over and over again. It's just that for the first part of the lab, you are changing the planet or the moon or the asteroid. Okay, that's all you're doing. Okay, so you're getting different data sets because you're changing to a different planet or a different asteroid or a different moon. For the second part, it's the liquid in which the bottle is submerged that we are changing. Okay, you start with gasoline, then you move to crude oil and water and so on. Okay, and in the third part of the lab, it is the volume. Okay, it's the volume of the bottle that you're changing, isn't it? 7 different bottle volumes. Okay, you can pick any 7. Okay, you change that, and each time you will need a graph at the end. You will need to plot a graph of the so for the first lab, you will need to plot a graph of the buoyant force against the acceleration, the gravitational acceleration. Gravitational acceleration corresponding to a specific planet or moon. Okay, so you will have to plot that and get the equation that explains the relationship between the two. Okay, and for the second lab, you will have to plot the buoyant force versus the density, because remember we are changing the liquid. So the liquid or the fluid in which the bottle is submerged has a different density as you change to a new fluid. And we want to know what the relationship is between the buoyant force and the density. Each time the buoyant force will be on the vertical axis, okay? Because it's the buoyant force that we want to explain. And then for the second lab, for the second part of the lab, the density will be on the horizontal axis. And for the first part, it's the acceleration, the gravitational acceleration that will be on the horizontal axis, right? Yeah, they call it AG here, gravitational acceleration. And for the third part of the lab, the buoyant force will be again on the vertical axis, but the volume of the bottle will be on the horizontal axis. Okay, and then you will need an equation for that, so a graph and the equation for that also. And as a reminder, you can, if you don't remember how to plot in Excel, I assume everybody remembers how to plot in Excel because you've done it several times for many of your previous labs. But if you don't remember how to get the equation that explains the relationship between the variables, you can find the explanation in the very first video that we made. Okay, it's posted on Blackboard, and you can find it on YouTube. So I think that's it. Are there any questions? No questions? All right. I'm going to stop recording, and you should start working on your labs, and then ask me questions as you go along, and I will help you.